Track A, Mathematics and Statistics, Part 1, Linear Algebra. AI has started creating everything from text to code to images to music and amazing videos as well. And while we think AI is generating all of this, it does not understand emotions, it does not grab the meaning of the text or code or any of that stuff. So, how is AI able to exactly do that? It is through numbers. Yeah, it is doing this through number manipulations. And what AI does is it takes all of those things, the words, the sentences, the images, the user data, the products, videos, code, any of that stuff, and converts it into a list of numbers in the form of vectors. We are going to see what these vectors are, but it's converting them into this list of numbers and performing two operations on them. One, measuring the similarity between them using some techniques and some formulae, and then it is trying to transform them like matrix multiplication. Both of these two we are going to look very much in detail, in depth, as we progress forward. In this deck, or part 1, we expect you to start developing that vocabulary as AIPM. Today, we are going to look at 5 concepts in depth. One is the data containers. Then we're going to look at dot product, cosine and Euclidean distances, the matrix multiplication, and the coordinate system. Finally, we'll touch upon why all of these matter for product managers. And we are also going to look at some misconceptions and some Q&A that will help us prepare for interviews. To start with data containers, the simplest form of data that you can imagine is a number, where you have a temperature or a price of a product and so on. That's the most simplest form, and it does not have a structure of its own. That's why it's rank 0. Then we have a vector. It's an ordered list of numbers. For example, if you have a person standing on a ground and you want to say where is he with respect to some origin of or some corner of the ground, you'll say, hey, he's 5 feet away from one side of the wall and 10 feet away from other side of the wall. So you put him on a graph or a coordinate system and say, hey, this is how far he is. So that looks like a vector. That is a vector for us. Then we understand what are matrices. It's a 2D grid of numbers, and this is nothing but a stack of vectors, one above the other. And if you talk about tensors, tensor is a generalized ND case of adding more and more axes. So if you have 3 dimensions for a particular use case, then it can be called a tensor. So matrix is a tensor, a vector is a tensor as well. Okay, let's dive deep on scalar. A scalar is nothing but a singular number. It could be a temperature like 23.5, a model's confidence or a probability score like 0.87. It could be the price of a product like rupees 499. Yeah, scalars are where the whole story starts, but nothing interesting in AI happens until these numbers uh, exist as an ordered list, and that's where vectors enter. Like we were talking earlier in an example where a person is standing in a ground, and we could specify where he is in the ground with respect to one corner of the ground using a coordinate system like x comma y. Okay, where x is the horizontal axis, y is the vertical axis, and are the other edge of the ground. We can position that person on the ground using x comma y. Now here is a mental shift that we need. A vector is simultaneously a point in space because it's x comma y, and it's also an arrow from the origin to that point. So vector has both a direction and a magnitude associated with that. Okay, and in dimensions, this is a 2 dimension, as in on a flat ground. If you put a point, we can say x comma y. But what if it was n dimensions? In n dimension, it could be 1536 dimensions as well. So that idea is being extrapolated. Now imagine there are certain movies that we want to use as a use case, where we want to recommend one movie based on the other movie, or we want to understand if two movies are similar. Okay, one, we could take examples and learn from them. For example, let's think of Die Hard as a movie, and there are two dimensions by which we are pointing them on this space of movies. Okay, one dimension is action, where we say how, to what extent this movie is a die hard or a hardcore action movie. Okay, Die Hard is a 9 out of 10 on that axis. Okay, for example, on the axis of romance, which is the y axis here, this is a 1, as in it hardly has any romance between the lead actors there. Then we have a Notebook, which is a pure romantic movie, and you see on the romance dimension it's very high, whereas on the action it's 1. Okay, that's why it's, this is x-axis, this is y-axis, that's why it's 1 comma 9. Mr. and Mrs. Smith, which is a movie about two people who are husband and wife, and them being part of two different spy agencies. They have a point of 7 comma 6. So if I were to identify which of these two movies are similar, I would have to look at the distance between them. Okay, and then say, hey, which of these two movies are similar in nature? And that's how your product recommendations come, that's how your movie recommendations come, that's how your song recommendations on Spotify, everything come. They identify, hey, which of these two songs are similar in nature by certain dimensions. And that's the entire idea of embeddings as well. If you are trying to embed the text in a particular space, we'll learn more about this in AI track. But for here, embeddings typically mean, hey, you're taking text like a movie, and you are putting it into a n-dimensional space, so that the system or the LLM understands this. That's all you need to understand by embeddings. What is an embedding? Embedding is the conversion of, or you're trying to transcode the text into a vector, n-dimensional vector. That's all you're trying to do. Okay, for example, in the previous example, we had movies which were two-dimensional in nature, but these in reality could vary anywhere from 512 to 3072 dimensions as well. Okay, that's why it's important for us to learn that every aspect of a particular text or a code, everything is a dimension here, instead of naming them. Okay, we are not going to name these dimensions because it's really not helpful. Even the LLMs don't understand it, so we only need to know the number of dimensions rather than the names of the dimensions. Okay, sentence embedding is exactly this, a list of 1536 numbers that tries to look at the meaning, or a sentence's meaning in space. Okay, forget the rest. All we need to understand is similar things sit near each other in vector space. That's all we need to understand. For example, in this case, these two movies have some commonality between action, between them, that's why they are close. These two movies have some relevance between them in terms of romance, that's why these two are close. But if you look at Notebook as a movie which is pure romance versus Die Hard, which is a pure action movie, both are very far. Okay, and matrix is nothing but a stack of vectors arranged one above the other. For example, if you had uh, a movie which you were trying to classify or position based on the action and romance as a dimension, it will have two dimensions. But what if there were 10 movies? Okay, it will form a 10 by 2 dimensional matrix for you. Okay, where 10 rows will be the 10 items or 10 movies, and 2 dimensions will be the 2 columns for that. So how would it look like? So if you were to think about how would it look like, it might look something like this. Okay, this is a big list of 10 items, and each item is like this: 1 comma 2. There is one movie which is Die Hard. Then there is one movie which is Notebook. Then there is movie Mr. and Mrs. Smith, and so on. Like this, you will have 10 items, and these are 2 dimensions for you. And that's what we need to learn about matrix. Matrix is a stack of vectors. That's what we just saw through an example. And then there is a transformation angle to that. So what happens, we need to understand a little about LLM models, or any other models that we are talking about. All these models are nothing but a neural network layer. And if you know about neural network layers, they are nothing but a collection of weights, and these weights are stored in the form of a big matrix. So when we talk about, hey, there is a DeepSeek model with 7 billion parameters, we are talking about total 7 billion weights in a matrix. Okay, we'll look at some of the examples as we progress forward. Okay, and that's all we are trying to say here in this slide. We are talking about, hey, same object, it plays 2 different roles. One is data at rest, on how we store this data, and then we have on how we are trying to perform some transformations to make sense of the data and proceed further. Yeah, and tensor is a generalized ND case of data storage or data containers. The more access you have, the more D's you can add. For example, a color image. If you know, color images typically have a view, something like this. So if there is an image, image would something look like this, where each is a pixel, and each pixel will have RGB color associated with that. So when we think about the dimension here, it's height, width, and 3 RGB channels. Okay, so each image or each pixel would be represented by the x-axis, the y-axis, and the RGB color. Okay, so this is 1 dimension, this is 2 dimension, and this is 3 dimension. So that's why this is a 3D image. And then we have a batch of images, for example, since this is for a single image that we saw. Okay, if we add another dimension, which is like let's say A, as a batch of images, so this becomes another dimension to it. So there we see this is 4D dimension to it. What does all this mean? What does all this mean? All we are trying to say is, when engineers talk about activation memory, like, hey, there is a DeepSeek 8 billion parameter model that we have, they are talking about all these multiplications. Yeah, that's what activation memory means. The activation memory means this activation tensor. They're saying that, hey, I need this much processing power to manipulate all these numbers, and that's where that numbering comes from. Okay, we look at these in detail as we progress further, but for now that's enough. Let's proceed further. In shapes, in matrices, one of the important things is the shapes. Shapes talk about how the data is structured in that particular matrix. And it's very important to understand this, because matrix multiplication, matrix transformation, everything depends on the shapes. Okay, there is a simple notation that we use to determine matrices. Uh, a matrices dimension, or the shape, it's rows by columns. That's how we say it. It's rows, number of rows by number of columns. So for example, if you had a matrix 3 comma 4, which is this is one, this is 1 row, this is 2 columns, so it is 1 by 2. Yeah, if we had another matrix, something like 3 0 4 1 2, 6. Yeah, this will be 2 rows, yeah, by 3 columns. So this will be a 2 by 3 matrix. And if we are trying to multiply two matrices, we need to ensure that the inner numbers are matching. If you are trying to add two matrices, the shapes should match as is. Okay, so that's the simple thing. And for example, how does the matrix multiplication happen? We can look at with an example. For example, if we had a matrix like 1 comma 2 3 comma 4, and we were trying to multiply this with another matrix which is 2 comma 4, we could do this multiplication here because this is a 2 by 2 matrix and this is a 2 by 1 matrix. This center numbers should match, only then the multiplication will happen. How does the multiplication happen? We take the first row and multiply with the first column, and that gives us the top number. So 1 2 is a 2 plus 4 2 is a 8, 8 plus 2 10, this is 3 2 is a 6 plus 16 which is 22. So this is how we arrive at the final matrix, which is 2, which is a commonality. We remove that, and then we have 2 and this one, which becomes this 2 by 1 matrix. We'll see more examples further. But what happens when the matrices do not match? For example, if you have a matrix 1 comma 2 3 comma 4, and you're trying to multiply this 1 comma 3, okay, this you can multiply with this you can multiply with this, but what will you do with the rest? We need a second number to be multiplied here, which is not there. So this does not match with the multiplication, and hence it gives you an error. Okay, let's proceed further. There are two simple actions that we do on matrices called transposing and an inverse. It's not really important for product managers, but it's good to know. Okay, so when you transpose a matrix from its current state, what happens is it transforms to a different shape. For example, if you had a, this is a 3 by 1 because there is 3 rows and 1 column, it is a 3 by 1 matrix. Now if you do a transpose of this, this is going to become like 1 2 3. So this is going to become 1 by 1 2 3, 3 columns, so it's going to become 1 by 3. So what you're doing is you're taking this matrix and transposing it into this format. Now if you had let's take another example to understand this further. Now imagine you had a matrix something like this, where we are saying you had 1 2 3 and 4. By transpose, what you're going to do is you're going to take this and put here, you're going to take this and put it here. So this becomes a transpose. Since this is a 2 by 2, the transpose also remains 2 by 2 only. Okay, we'll look at more examples when we try to work out the IPython notebook in Google Colab. But here we're gonna look at one more thing called the the most famous equation in deep learning, because all our deep learning models are trained on this equation. What happens is we take an input vector called x, and we transform it with weights. Weights are the learning parameters that the model learns, and we add it some bias so that we can predict or get to the output y as minimal as possible. What we are always trying to optimize for is the weights, while trying to reduce the error or the bias. Okay, that's how a machine learning model or a neural network model is always trained. That's why they call it the most famous equation in deep learning. Yeah, we'll see a tiny worked out example in the next slide. This is how it is. So we see a weight called 102011, which is a 2 by 3 weight matrix, and then we have a x, which is the incoming input, which is 10 20 30, and we have a bias. Now how would we multiply this? 1 into 10 plus 0 into 20 and 2 into 30 plus 0 into 10 and so on. That's how we would multiply them. See, it is shown here. So we get 70, 50, and then we have a bias matrix that we need to add because this is wx plus b. So 1 plus 70, 5 plus 50, we get 71 comma 55. Yeah, so that's how the shapes take shapes come into life, okay, for matrix multiplication, addition, etc. And with that, we come to the next topic, which is the dot product. The most important operation in AI is a dot product. Okay, how does it work? Geometry. There is a equation a dot b is equal to the norm of a, the norm of b into cos theta, the angle between a and b. Whereas in algebra, it's much more simpler. A dot b is equal to sum of the individual terms of ai multiplied with individual terms of bi. Okay, that's how we arrive at a dot p. Now if we had to get the uh, cos theta value, all we are going to do is combine these two equations and we will get onto something. Okay, this is not really visible. So if we were to come up with the formula for cos theta, then it would look something like this: a dot b by norm a with norm b. Okay, and in this place, ab could be replaced with this. So we end up with an equation that looks something like this: cos theta is equal to sigma of ai bi by norm a norm b. We're going to look at what's the formula for norm a and norm b also very soon in the next slide. Okay, but why are we doing this dot product? Why are we doing this dot product in the first place? Because the dot product tells us the alignment score between the two arrows, or uh, which is a dot and b dot. So in a space, this tells us, hey, how similar are these two? To do the similarity, we just do a dot b. Yeah, so that's what it is. Yeah, if the two arrows are aligning in the same direction, the larger positive value we'll get. If they are orthogonal in nature to each other, then the value will be 0 because cos theta of cos 90 is 0. If they are in opposite direction, we'll get a negative score. Okay, what is a good terminology to explain here? Imagine there is a shopping cart that you've been using. Okay, and you're in the shopping mall. Now imagine you push it in the same direction, the cart moves in this. But what if you pull it in the opposite direction? It's going to move in the negative direction, which is pushing backwards. But what if you push it sideways? It will not move, it will not budge, because the wheels are aligned in the front or back direction but not sideways. So the effect is going to be 0. So that's how the dot product measures. What it measures is how much of your effort is counting, or how similar the two vectors are. Okay, and here is an example that we were earlier trying to do: Die Hard, and let's do a dot multiplication of Die Hard and Mr. and Mrs. Smith. If you remember, Die Hard is a pure hardcore action movie. Mr. and Mrs. Smith movie is a little on the verge of romance and action. Okay, so now if you do a dot product, you get 69, saying that hey, they are a little closer. But if you do Die Hard and the notebook was a pure romantic movie. So if you do a dot product, you get a very low score because they are far away from each other. So the dot product brings a very low score here. Okay, how did we do this dot product? We use the formula that we saw earlier, sigma ai bi. So for this, what would it look like? 9 into 7, which is 63, plus this is 6 into 1, which is 6. So this gives us 69 score. Now if I do the dot product here, 9 ones are 9 plus 9 ones are 9, which is 18. So these two, the score here is low because they are from different genres. Okay, that is how the dot product worked in your algebra. Now attention is dot products, because every token that we parse in is gonna check, hey, what is the next relevant token for me? Because LLMs are nothing but next token predictors. So they're gonna ask, hey, what is the next relevant token for me? And they're going to do the dot product, get a value, and say, hey, is this the next highest value? Yeah. And if it is, then it will get the response, it will predict as the next at important word. Now the dot products are the scores. They decide which tokens should they attend to. Attention is literally an alignment ranking here. Okay. So if you imagine that, hey, there was a token that came in, and we are trying to predict whether this is the closest token or this is the closest token, we see that, hey, these two are having very similar this compared to these two. So it will try to predict this as the next word available. Okay, that's what an LLM is all trying to do. Okay, at scale, GPT computing attention over a 2000 token context is equal to millions of dot products per layer. We are going to look at all of this in week 4, which is almost like 20 days away, and we'll look at how the total millions of computations take place. But for now, remember that every input that comes as a vector and it passes through an LLM, which itself is nothing but a matrix. These two are multiplied, you get a score through a dot product or like that, and you get a score. If the score is high, and that's the next best word to be predicted, attention is achieved, and that word comes out next. If something else is in LLM's mind through embeddings, it will have some other word predicted. So that's how the attention is retained in a big token context. So the larger the attention that you need or context you need, the larger the dot product multiplications need to happen. That's all you need to remember. The more the dot products are to be multiplied, or matrix multiplication need to be done, the larger the memory would be consumed. Retrieval is also all about dot products. Now if you remember, many of us would be talking about, hey, we need to implement RAG, we need to ensure that the context is not lost, that data needs to come only from specific documents through implementation of RAG. Hey, there is a RAG pipeline and so on. at at the core, all they are trying to say is, hey, i have a I have a database, and all queries need to come only from that database, because LLMs are generally trained on universal data, and they do not have specific information about your product. So LLMs are trained on the world data, and they have knowledge about that. But you know about your customers, and you have stored your customers' data in your specific databases, and you're saying that, hey, whenever there is a chatbot conversation happening with a particular customer, in that chatbot conversation the data only should come from this repo. You typically try to implement something called a RAG pipeline, retrieval augmented generation, as a pipeline. Okay, so what's happening when it tries to retrieve the data is, LLMs are at the center. Your queries are passed to LLMs. LLM has a text or a token that needs to go and search in this database. Typically, you would have implemented, uh, instead of having implemented a database like rows and columns of data, you would have implemented something called a vector database. Instead of SQL, you would have SQL database, you would have implemented something called a vector database. In vector database, every token is parsed, stored as a vector in a vector space. Though I'm saying it is two-dimensional here, vector DBs can have their own dimension. It could be 1536 dimensions, it could be 512 dimensions also. That depends on how did you do the embedding, etc., which is a topic for a future video. For now we need to understand that, hey, the vector database's job is to find the relevant documents to your query. So when a chatbot conversation happens and LLM gets a query or a text, and this data needs to be retrieved, all you're trying to do is find the similarity between two documents and return that as a response in the chatbot. Okay, and that's what RAG pipelines relevance also means. Yeah, dot product is what we are executing, and if the dot product score is higher, we want to retrieve that data and return it to the user as a response. That's what retrieval does. Okay, so here the last statement is very important. So if the bot retrieved the wrong document, it basically means the wrong vectors were scored the highest. So imagine there were two documents, and these two documents were closer and they were supposed to be retrieved. But instead, some other document which is far away from this was retrieved. It basically means that the wrong vector was scored the highest. And recommendations are nothing but dot products. Okay, when user gives an input like, hey, user loves more action, less romance, and if you had two movies like Die Hard and The Notebook, you would do a dot product with the user's query and your data that you had, and you'll score them. Okay, for example, 8 2 against your 9 and 1, you'll do a dot product, you'll get a score of 74 with Die Hard and a score of 26 with Notebook. So ideally, what would you do? Since user loves more action, you would recommend Die Hard. Yeah, and that's the simplest version of highest dot product wins here. Yeah, Netflix also does something very similar for recommending movies based on users history. It might not be two-dimensional like this where there is only action and romance. The dimensions could be 1500, 500, 1536 or more also. Yeah, this brings us to the next big thing. We did the dot product, but how do we tell if the two things are similar or are they just close to each other? Yeah, there is a big difference between these two, and that's what we are going to learn in this third part. Okay, the cosine similarity, earlier we saw a dot b is equal to a norm b norm into cos theta, or cos the cos of cosine of angle between a and b. Now cos of or cosine of AB will look like a dot b divided by a norm and b norm. Yeah, the dot product after ignoring lengths is cos theta. So what does this say? Hey, not just the magnitude, but direction is more important to me, or direction is the only thing that's important to me, because I'm trying to measure the similarity of two things, not the distance between them. Yeah, while Euclidean distance, or L2 as we call it, is the distance between 2 points in space. Yeah, and how close are they to each other, or how far apart are they from each other? That's what we are trying to measure. And here magnitude matters. Yeah, not, this does not take into consideration the direction. How do we do this by hand? Let's consider there are 2 points, A 1 2 2, B 2 1 2. If you do a dot product, you'll get 8 as a score, and you take A norm B norm, which is the square root of sum of the individual numbers. So A would be square root of 1 plus 4 plus 4, because we are taking squares of these numbers. It will be 9. Square root of 9 is 3. Similarly, B, square root of 2 square plus 1 square plus 2 square, which is square root of 4 plus 1 plus 4, which is square root of 9. You get 3 again. So cosine will be A dot B, which is 8, divided by A norm into B norm, which is 3 into 3, 9. You get 0.89, which is a very high similar score. Yeah. This gives you the semantic similarity score. We are saying that, hey, cosine is telling us how similar these two things are. They are very close. Okay. We'll look at many more demos also. Here, let's take an example. In this example, we are looking at A is a document about pricing, and then there is B as a document, which is also about pricing. Okay, then there is a C document. It is totally entirely different and it has something else. Okay, now if you take the cosine between A and B, which is between this A point and this B point, we get 1 as a score. Why would we get 1? Because they are in the same direction. Yeah, same direction typically means you'll get a score of 1. It means they are same topic. But if you take the L2 distance, you'll find that, hey, 8.49, it's very far away. These two are very far. Okay, but if you take the cosine between A and C, they are orthogonal. So cos 90 is 0. You'll find that the orthogonal value between A and C comes at 0. Okay, whereas L2, the score between A and C will come as 4. So these two are closer. Ideally, these two should be having. So this would mean that A and C are closer to each other. Should I give C as an output? Ideally, no, because we are expecting the same pricing documents to be surfaced if I'm searching for pricing documents. Yeah, so that's why text search uses cosine, because Euclidean only makes the unrelated docs look closer. Okay, there is a spelling mistake. The unrelated docs look closer to than the same topic B. Okay, because the length polluted the answer. But if you do a text search wants same topic, not same length. Okay, that's where cosine helps us, because it's encoding, the direction is encoding the topic and meaning here, and magnitude often just reflects document length or document frequency or a term frequency. Okay, where Euclidean does belong, if you were trying to do clustering of objects which are closer to each other, etc., then Euclidean will make sense. In the context of text making sense, I mean when the text has been encoded into a vector and you finding similarity between vectors, then the cosine helps. But if if the data, like people living on a map, were transcoded into coordinates like latitudes, longitudes, and you were trying to find the person closest, then you would use a Euclidean distance instead of a cosine. So, rule of thumb, if you're searching for meaning, cosine is the choice of measurement. If you're looking at measurements and distance, how far is a particular thing from another thing in terms of distance, then Euclidean is the right measurement. We will not get into normalization because this will deviate. We'll come back to this in one of the future lectures. This brings us to matrix multiplication. Why is matrix multiplication important? Because just like we saw the dot product of A and B, where A and B were just two vectors, were multiplied to get the cosine angle, matrix multiplication is important because all that we do is tokenization, and once tokens are created, we put them into vectors, and these vectors pass through LLMs, and LLMs do the compute to tell what is the next word that needs to come out of that system, and that word, if it has the highest attention score, then it comes out, and like that next word is predicted. Okay, every other word is predicted. So everything that we are trying to do in LLMs is purely matrix multiplication. That's all we are trying to do. Yeah. So every output cell is one dot product. Okay, for example, if you had two if you had two let's say matrices A and B, and you are trying to multiply these two, like we discussed earlier, how would we do this into this plus this? For example, 1 into 5 plus 2 into 7. Yeah, 1 into 5 plus 2 into 7. Now this one multiplied with this one gives you the second word. Yeah, second cell output, third cell, fourth cell, or this will be the fourth cell. Okay, like this you get all the 4 cell data individually, and you get this. So this is a 2 by 2, and this is also a 2 by 2. We saw that earlier that these two need to match, and once you match that, this is the final matrix that it forms, 2 by 2. Yeah, that's how we got this 2 by 2. Okay. A machine that reshapes space in chains. Matrices typically undergo two things. One, they undergo transformation, like we earlier saw. They rotate, they stretch, they squash, they shear. What we are trying to say is, hey, matrices undergo transformation, either in shapes or in terms of addition of numbers, reduction of numbers consistently. And it looks at composition, which basically means, hey, layer after layer of transformation, what happens to the uh, uh, matrix towards the end. Yeah, these are the two mental models that you need to remember as we go forward. Okay. And why is this the whole game? Billions of weights that we saw in GPT class models are organized as matrices, hundreds of large matrix multiplications to generate one token, and your API bill is nothing but a matrix multiplication bill. Okay. A very deep dive will happen on this in the uh, AI track. Watch out for that track. That's gonna have a very precise and very detailed explanation of how many matrix multiplications happen for a given model size, for a given input token, and so on. Okay, because that's how the number of matrix multiplication calculations happen. That's how the GPU sizes are calculated. That's how your API builds are built as well. So watch out for that space. And why GPUs and why NVIDIA? Each output cell is an independent dot product that we just saw. Yeah. And thousands of them are being executed in parallel. Okay. We need to parallelly execute such huge workloads. And GPUs help us these do and GPUs help us do that. GPUs have thousands of small cores, and they are designed to execute or do these dot products in parallel. And ideally, GPUs, graphic processing units, as the word says, was developed by NVIDIA for game playing, because there also you're doing a lot of matrix multiplication to explore environments, to move the character along the space, to rotate the character and do everything. Everything is a dot matrix multiplication there. Okay. While CPUs only have dozens of powerful cores, CPUs have thousands and even more of them. Okay. And this is the reason that NVIDIA grew faster, because they were able to do many more dot product multiplications or matrix multiplications at scale by 10x and 100x over CPUs. And that's why the stock price of NVIDIA is also exploding, because we need more and more GPUs to generate more and more tokens faster. Okay. Yeah, we'll skip this, the identity and the inverse matrices, because right now it's really not important at this pace. We'll come back to this if we have time. The coordinate system is nothing but the dimensions put in the core in a three-dimensional space or a four-dimensional space. That's how we are seeing it. So what happens with vector space is, we saw that, hey, if in the example of movies, we saw that, hey, one movie was here, one movie was here, and one movie was here. Okay. Now if I had to identify the closeness, we were doing dot matrix multiplications. Now this is just two dimensions. Okay. But what if I was trying to compare or identify which of the two recipes in the world are similar to each other? So first I need to take one recipe and identify how uniquely will I identify all of this. So there could be maybe 600 dimensions, for example. Yeah. And I take another recipe. I see how many dimensions I can put it. Ideally, I will be evaluating each recipe along the same dimensions. So there is 600 dimensions, for example. Okay. Now, when we try to identify the dot product between these two, we will have a 600 by 600 dimension matrix multiplication or an output. Okay, that will be our output. Okay, that's why the embedding dimension is important. Yeah. So how many dimensions are required? This is the biggest challenge. We never know. Movies, we saw two dimensions helped. One is the action, one is the romance. Two dimensions helped. For recipes, maybe 600 helped. For text, we are not sure. These days, anywhere between 512, we saw that earlier as well, 512 to 3052 dimensions are used to encode text, and in the vector space or vector database, and retrieve closest text based on these. Okay. Another dimension that we are talking about is, what if a couple of dimensions are dependent on each other? Will that really help me predict the next token with each other? Is a big question. For example, if I had uh, uh, one dimension and two dimension, and this dimension was dependent on the other, like in this case we have price USD and price INR. Both are dependent on each other, because if I know the price of USD, I can multiply it by a certain number and arrive at the price in INR. So these are dependent variables or redundant variables. Ideally, when we have a dimension, we want each of those dimensions to be independent and not dependent on each other. Database costs increase as the number of dimensions increase. Okay, so you're going to your engineer and you're saying, hey, vector db cost is scaling very faster, can we do something, can we cut down on the dimensions, is what you're asking. Yes, there are some processes called Matrices embeddings that help you truncate from 1536 dimensions to 512. There are also techniques called principal component analysis. So that helps you reduce the number of dimensions that you have, and so that you reduce from 1536 to 512 dimensions. If you reduce also, you're gonna do a lot of cost savings. But will that trade-off actually pay off is something that you'll have to validate. Okay, that validation is done through A by B tests on a trusted golden data set. Okay, we'll talk more about this as we explore this. So yeah, that's all about concept payoffs. Now let's understand why these topics matter for product managers. We learned that embeddings are nothing but vectors put in a database. Okay, every semantic feature that we are going to ship, whether it is about searching, data deduplication, clustering of data, recommendation on images, music, videos, or you're going to implement a RAG pipeline to do a knowledge based discovery, everything rests on vector geometry. Okay, when quality disappoints, the geometry is the suspect number one. For example, if your embedding model choice was wrong, your normalization was not done correctly, your domain fit was not tested, geometry is to be put on place. You need to check the size of the embeddings, you need to check how the calculations were done, how the RAG was implemented, and everything. Okay, similarity search depends on cosine similarity. We just saw this throughout this deck. That's the only thing that we saw. Yeah, if you want similar search for text, it has to be based on cosine similarity, nothing else. Recommendation systems compare vectors. We even saw that if user has a certain preference, and then we have certain item, um, and we have a certain item with us, we would calculate the dot product between them, and we will find out the affinity or closeness between those two through matrix factorization, and we will identify the score. If the score is higher, we will say yes, recommend that particular item. Yeah, recommend that particular item. So recommendation systems use or they use vectors for comparison and then output that result. RAG retrieves nearby embeddings. Correct. This is important to learn for the very reason that when you implement RAGs, you need to ensure that uh, the wrong documents are fetched because there weren't the right vectors. If there were right vectors, you would have gotten the right output. Okay. um, you can now ask which the query embeddings, the docs, or the distance metric, what went wrong. Okay, you just need to identify which of these went wrong. Okay, cost conversions are shape conversions. We saw this also. The number of tokens, the dimensions and layers is all about the compute power required. Okay, when we say hey 70 billion parameter product, we are talking about this here in this layer size. Okay, how many dimensions would we need, how many tokens are being passed input as an input, that will all form to uh, create the compute layer. So the larger you want the number of input tokens, the larger the model for attention span, the higher the infra cost. Yeah, remember, you don't have to do this math at work. Okay, engineering team, or there are standardized products, LLMs, everything that do the work for you. But when there is something that you need to choose in terms of model, in terms of compute power based on the input size, everything, product managers need to understand how do I take a decision there. Let's look at some interview questions that you might get as part of your AIPM role. Question like, hey, what is cosine similarity and why is it preferred over Euclidean distance for text embeddings? And we understood that cosine measures the angle between two vectors, direction only. It tells whether the two texts are similar in nature, whereas Euclidean distance measures in straight line, which brings only the measurement or the length or distance between them. So for text, direction encodes the topic or meaning, and hence it is more important. Whereas for all other tasks like identifying if two clusters are closer to each other, we only need Euclidean distance. Another question that could be asked, hey, explain the dot product to a non-technical stakeholder. In simple sense, the dot product is an alignment score between two arrows. Yeah, if two arrows are pointing in the same direction, that's a big positive. If they are orthogonal or at a 90-degree angle, they are unrelated, so the score is 0. And if they are in opposite direction to each other, we get a negative score. And we saw a real life example of pushing a shopping cart. If you are pushing it in the same direction, it moves forward. Yeah, that's a big positive. If you push it backwards, it goes backwards, which is negative. If you pull it, it goes backwards, it's in the negative direction. And finally, if you push it orthogonally or in a 90-degree angle, the wheels are aligned to go forward or backward, it will not budge. So there is no effect or uh, a result of you pushing it at a 90-degree angle. So the dot product is 0. Why are GPUs good at deep learning? We know that deep learning is a overwhelmingly matrix multiplication, and every cell of a matrix multiply is an independent dot product. We just saw that. Okay, and we need thousands of small jobs with no dependencies on each other, and GPUs have those thousands of small cores built for exactly that parallel pattern or parallel processing. CPUs have a fewer powerful cores optimized for sequential work. Same reason that they were good at 3D games. Yeah, and hence GPUs are good at doing deep learning tasks. An engineer says the retrieval index uses normalized embeddings with dot product search. What does that imply? Yeah, normalized typically means that all vectors are scaled to 1. So dot products equals cosine similarity. Ranking is purely by direction and unaffected by document length. It also tells me that any cosine was a dot product debate for this index is moot. Moot as in it doesn't matter. So in this context, what's happening is when we try to normalize all the vectors to a length of 1, the max length that you will get is 1. Everything will fall between 0 and 1. Okay, and when you do the dot products, the multiplications are a little faster, but at the same time, you need to remember that these rankings are purely by direction. We want to cut vector database costs. What are the levers on the embedding side? So on the embedding side, like we looked at in the previous slides, we can reduce the dimensions to reduce the vector DB costs. And that can happen through applying either PCA, which is principal component analysis, or Matryoshka truncation technique, where the dimensions could be reduced from 1536 to 512, or from 3072 to 1536. And we can quantize those stored vectors or shrink the corpus via deduplication. All that can be done as well. So shrinking the corpus via deduplication typically means that you have a lot of duplicate text, and you're trying to reduce that corpus size by deduplicating that text. Okay, if each trade that you do, each trade recall for cost. So what's happening here is you're trading the recall for cost. Gate the change on retrieval metrics against a golden set rather than eyeballing it. So always ensure that whenever you're trading recall for cost, uh, it has to be very precisely done. You have to test it thoroughly before you deploy it in production. The cost could be reduced, but it might start pointing in wrong documents and fetch you the wrong documents. So that's a trade-off that you need to do when you're reducing the dimensionality for vector databases. Lastly, hey, what does dimension mismatch mean when an engineer says a pipeline is broken? It's simple. There were two matrices or two arrays whose shapes didn't line up for multiplication. For example, a 3 by 4 array was fed into something like 5 by p or 5 by 6, and they were trying to multiply these two, and they were having the wrong embedding size, or a wrong batch shape, or a model swap that changed the output dimensions, and so on, which is why changing embedding models mid-flight require a total reindexing of data. So ensure when you have embedding created in the first time, do not try to reduce the embedding size or dimensionality and so on, which would typically mean that you are trying to reindex the data, without which your model is going to break. And we come to the conclusion of the recap, or we come to the conclusion of this part 1 of a long series on this track A on mathematics and statistics. These are the two things that we learned today. Okay, we learned that AI measures angles between two vectors through similarity, and we are trying to transform them, which is through matrix multiplication, and we do this over and over to achieve what we call next token prediction. It could be generation of text, code, image, music, video, any of that stuff. Okay, and in this part we saw what were containers. We looked at scalar, vector, matrix, and tensor as the containers. We looked at what is a rank, the structured containers were given ranks. So we know that scalar is rank 0, vector is rank 1, matrix is rank 2, and tensor 3 and above. Okay, shapes, we saw what is shape. We also looked at a notation of m by n. We looked at what is a dimension mismatch when we are trying to do matrix multiplication. We looked at what is transpose, how transposing matrices changes the row by column dimensionality. So if a matrix was 3 by 4, if you transpose, you get a 4 by 3 matrix. And we looked at the most famous equation in AI world, which is y is equal to wx plus b. Y, which is the output, is equal to weights into input, which is x, plus bias. Then we looked at similarity. How do we calculate similarity of two vectors? We did dot products. We looked at what is alignment between those two vectors. We looked at two calculations. One, calculating the similarity using cosine, and calculating the distance between 2 points using Euclidean distance. We also looked at how normalization is done on these. Yeah, normalization we will look at it in the future as well once more. Then we looked at attention retrieval and recommendations using similarity as an example. Then we looked at transformation, where we looked at how matrices are multiplied. We looked at composition, and we also looked at what happens if you cut down on embedding dimensions. Okay. Lastly, we looked at coordinate system, which was about vector space. Uh, Linear independence, we looked at each dimension needs to be linearly independent of the other dimension. If there is a relationship between them, we might not get the best embeddings and LLMs created. And what are the two techniques to reduce the dimensions? We spoke about Matryoshka and PCA, which is the principal component analysis. If you can explain each term with a 2D drawing, you have understood this module, or you have understood this module.